We will now have a look at electrical energy storage. To dive deeper into electrical energy storage, I first of all want to go through some kind of concepts of capacitors specifically, in order to make you familiar with the way how electrical energy storage functions. So for this, you have to know what you basically might recall from school, that electrical charges with the same sign repel each other, while electrical charges with the opposite sign attract each other. Therefore, you will have a situation like this. You will have, for example, a positive charge and a negative charge here. You will now notice these lines here. These lines are actually illustration for the so-called electric field. This electric field signifies that these charges exert a force on one another, and this is illustrated by these lines. The direction of these lines is given by the arrow. So the arrow signifies the direction in which this force acts, and the density of these arrows. So the number of arrows you have shown here, or the number of field lines to be more specific, shows you how strong this electric field is. So all of these lines together describe this so-called electric field, what I just introduced. Now, the strength of this electric field is given by the electric force which acts on a charge Q. Therefore, also the definition that the electric field E is the force which acts divided by the charge. And this will give you a unit of volt per meter. And please don't worry that it's very physical here. I just want to give you a few key concepts and one specific formula in the end, on which you will be able to recognize a lot of trends for these capacitors. So for now, we can say that the stored energy in an electric field depends on the one hand on the voltage, because the voltage you can find here in the electric field strength, and in the distance r between the charges. This is why you have a meter here in the denominator. You can describe it in a scalar form as well, as a force acting between two charges. And this would be that the force is 1 divided by 4 pi epsilon 0 epsilon r, where epsilon 0 is the vacuum permittivity and epsilon r is the relative permittivity, times the charges multiplied divided by the distance between the two charges squared. We will soon see what this mysterious value permittivity actually tells us. But for now, please just recognize that this scalar form shows a dependence of the electric field and of this force, depending on the charge you're having, depending on the distance between the charges, and depending on this specific value, what we call the relative permittivity. Now, let's go deeper into what a capacitor actually is. The charge stored in an electrical system is expressed by the so-called capacitance. The capacitance gets the symbol C. The capacitance is basically, as I call it here, the number of charges stored. Therefore, it expresses how much energy I can store in the system. And the capacitance C is Q, so the number of charges basically divided by the voltage. And this will give us a specific value in so-called Faraday. Faraday is the unit for the capacitance. And please make a clear distinction here that capacitance is used to describe circuit elements with different voltages, which are separated by non-conducting materials. Capacitors are arrangements of two opposite electrodes separated by non-conducting material. So this is please a difference which you should keep in mind here. So the simplest form of a capacitor, I would say, is a plate capacitor. So you simply have two flat metal plates which are sandwiched against some medium in the center. Now, we make a very simple assumption that this plate you're looking at that we will ignore that it has some edges and we will just look at its basal planes. So we will say that this area of this plate here has much more area than this tiny edges here. And this is what we would call a homogeneous arrangement. And now the capacitance of a parallel plate capacitor can be calculated more simply than the previous formula, simply as epsilon 0 epsilon r times A divided by D. So we see that the amount of charges which we can store in the system, or the amount of energy we can store in the system, is now given by this relative permittivity, while the epsilon 0 is the permittivity of the vacuum, so it's a constant. It's given by the area of the electrode, and it's given by D, which is the distance between these two electrodes. And now more specifically, the energy content of the capacitor is a value which also takes the voltage into account. So the energy content stored in the capacitor is 1.5 times capacitance times the voltage squared. And if we use the formula from above, we get this corresponding formula here. For all the following analysis, we are always assuming an ideal capacitor. So we are neglecting that we have ohmic or inductive properties of the plates, of the connectors, or of the dielectrics. And this is just something for the experts among you to keep in mind. Now, what is this mysterious value of relative permittivity? So permittivity defines the propagation of electric fields through the medium. So therefore, we have a direct influence on the electric field, and because it is basically a force per charge. So some non-conducting materials actually have a high resistance towards electric fields. These are called dielectrics. In principle, how these dielectrics work is that the material can form a dipole. A dipole is basically a molecule which has a certain localized charge, but it's orientable. So the molecule can turn and therefore create a small electric field itself. By creating this small electric field itself, it can orient opposite to the external field and thus oppose this field to counteract this external field. And the better a molecule can do this, the higher its relative permittivity is. Here we have an overview of a few materials which can do this very good or very bad. Actually, vacuum permittivity is regarded as one close to air, simply because typical molecules which you find in air, like nitrogen, oxygen, and so on, they cannot really resist this electric field. In the same group is, for example, Teflon or PTFE, polystyrene, polypropylene, or for example, paper. Notably, water takes a very interesting point here, because water is also a dipole. In water, the oxygen likes to attract electrons much more to itself. So the two hydrogen on the side, they have a partially positive charge and the oxygen a partially negative charge. By this, the water molecule is able to orient and therefore resist an external field.